Last time we were talking about solutions, different parts of solutions. Remember, a solution is really made up of two parts. That's the solute and the solvent. The solute is the smaller part of the solution, is typically the thing that is dissolved in the larger part, which is the solvent. In a lot of cases, water is a solvent, but as we talked about, water doesn't always have to be the solvent that is used. And in some cases, it actually is not the best solvent to use. And we talked about the idea of like dissolves like. So things that have similar intermolecular forces, they're able to interact really well with one another. We talked about equivalents. We also talked about electrolytes. Electrolytes, again, are things that basically will conduct electricity when they dissolve in solution. The reason they're able to do that is because they do create ions. The ions there are the things that will basically help kind of complete the circuit and allow electricity to be conducted. There's strong electrolytes, which 100% break apart in solution. There's weak electrolytes, which mainly stay together in solution, but do create a little bit of ions. Thus, they're able to conduct electricity, not as well as a strong electrolyte. The way you can tell the difference between the two, one of the main ways is the arrows that you see. If you have sort of a one-way arrow heading to the product side, that typically is your strong electrolyte. If you see arrows heading in both directions, that's a reversible reaction. That typically means that's a weak electrolyte and will mainly stay together in solution. There was also non-electrolytes, which will dissolve in solution. They really won't conduct electricity because they basically don't generate any ions in solution. So because there's no ions in solution, no electricity will be conducted in those cases. We also talked about equivalents. Equivalents are related to basically the charge, and it is actually the number, regardless if it's positive or negative. And we kind of use equivalents as a way to demonstrate the sort of concentration of things like IV solutions. And in terms of their charges, so for example, something at a -2 charge, we could say that in 1 mole of it, there are 2 equivalents, and really use that as sort of a conversion factor. We then at the very end, I believe, got started talking about some other type of concentration units. The first one that we talked about was sort of a percentage unit, which is a mass percent. And mass percent is the mass of the solute divided by the mass of the solution. And it's important in that one, as we talked about. Where's that? Not too far. The importance of this one is the bottom of that equation or formula. We do want to make sure that we do get the mass of the entire solution. Very common, these type of problems, the solvent and the solute sort of masses are separated from each other in the actual problem. So you do want to make sure you add it. So it's very common that people will sort of get just the solvent instead of both of the solution and the solute and the solvent to get to their solution. Remember as well that in sort of these percentage sort of concentrations, we can kind of convert them into like a conversion factor by assuming 100 grams of solution. So for example, the example I think I did last time there, if we had a 4.5% by mass solution of sodium chloride, basically that means you have 4.5 grams of sodium chloride in 100 grams of solution, or in 100 grams of solution, you have 4.5 grams of sodium chloride. Also a reminder that the solute is the name of the solution, so that typically helps out and trying to figure out which one's the solute or perhaps a solvent. Any questions on the stuff we sort of talked about, I think, last time? Okay, so if I'm not mistaken, I think this is sort of where we laid up. And let's talk about another sort of percentage concentration, if you will. This is percent volume to volume, which is sometimes abbreviated percent V to V here. And that means obviously volume to volume. And if I get the actual writing part, I think that works better. There we go. So that basically is volume to volume here. And in this case, it's actually kind of like milliliters over milliliters is typically what we use it as, unlike mass to mass where we do grams to grams. So this is typically milliliters here and milliliters. And usually in 100 milliliters of solution. So You could kind of do the same thing if you were given a percentage like 4.5% by volume, say it was calcium chloride. So again, you could turn that into sort of a usable kind of conversion factors by assuming 100. And that would mean in this case, you would have 4.5 milliliters of calcium chloride in 100 milliliters of solution. And again, because it's volume to volume here, we're using milliliters and milliliters, which are obviously volumes. Or again, you could flip it around and use 100 milliliters and 4.50 milliliters of calcium chloride. That would be 100 milliliters of solution. And again, we could sometimes, really treat these problems kind of like a dimensional analysis problem, conversion type problem. You could also plug and chug into the formula as well. So this is very similar to mass percent, except mass is grams over grams. Volume is obviously milliliters over milliliters. And one final sort of percent concentration that we sometimes come across, and this is percent mass to volume. And mass to volume, which is what M over V stands for, mass to volume. It's basically how many grams there are in milliliters. So again, here it is the grams of solute, the smaller part of a solution, divided by the milliliters. And it's kind of like molarity, grams per milliliter, if you will. Not molarity, I'm sorry. It's kind of like density there, grams per milliliter. And in this case, the units really don't cancel out, but we do leave it usually as percent M to V. And just like the other two that we saw there, again, if you have that 4.50% mass to volume calcium chloride solution, what that would mean in this case is you had 4.50 grams of calcium chloride in 100 milliliters of solution, or in 100 milliliters of solution, you had 4.50 grams of calcium chloride. So again, you could just convert this into really some conversion factors here to use in problems. So all three of those things are very similar. We have our percent mass to mass, we have our percent volume to volume, and we have our percent mass to volume. And these are, again, ways to represent concentrations of different solutions. Really, the only one that's sort of, particular, or you do have to be careful of, is the first one. Again, that bottom mass does need to be the solute and the solvent and the mass of the actual solution together here. All right, so why don't you take a second or two here and see what you come up with. What is the mass to volume percent of a Br2 solution prepared by dissolving 12 grams of Br2 in 250 milliliters of a carbon tetrachloride solution? So take a moment or two and see what you come up with here. 12 grams of Br2 here. We're going to dissolve it in enough carbon tetrachloride to make 250 grams of solution. That tells us that the Br2 is our solute. Again, usually the solute is the smaller part of the solution, the stuff that will be dissolved. That means that carbon tetrachloride in this case is actually our solvent. And we obviously made 250 milliliters of solution. So this is percent mass to volume. And that is the mass of the solute, which is 12, divided by the volume of solution, which is 250 milliliters, times 100% in this case. And we end up with 12 divided by 250 times 100. We end up with 4.8%. And again, typically here we would leave it as percent, and also very custom to include the M over V, which means mass to volume. So we know really what that percentage means. You could also put Br2 if you like at the end as well in terms of our values there. Any questions on that calculation? Now, This is a very good example we were talking about just a second ago that, in this particular case, the solvent's actually carbon tetrachloride and not water. And why would that be? Well, if we look at really what we're dissolving here, this is Br2, which looks something perhaps like this. This is a non-polar molecule, which basically means that it is going to try to use dispersion forces here as its main sort of source of way of interacting with other molecules. And if we wanted to use something like water as our solvent, looks like this. Water here is a polar molecule, and it is negative and positive at the hydrogens. Something like water, like we talked about, is actually going to be using hydrogen bonding. And these two, if they wanted to interact with each other, really don't have a way to interact well with one another. So water would be really a bad solvent in this case. They actually would separate out from each other. Again, it's that idea of what we talked about, that like dissolves like. Now, if we take something like carbon tetrachloride and we just kind of sketch the Lewis structure really quick, it looks something like this. Maybe, there we go. This is a symmetrical geometry. Everything on the outside is the same. There's no dots. This is a non-polar molecule. So this guy as well would be using dispersion forces as its main source of interaction, which is good because our Br2 would also be using the same sort of interaction. Now, when we kind of put these two guys together, everything is good in that case because they're both using basically the same type of interaction. Again, that like dissolves like. Again, they're able to interact really well with one another because they're basically doing the same interaction that Br2 would do with another Br2 is the same interaction it would do here with the carbon tetrachloride. And that's why, again, in this particular case, the solvent was not water because they would actually just separate out from each other. You would actually get two layers. They really wouldn't mix to make a solution. Any questions on that there? Okay. So why don't you give this one a go, calculate the grams of KCl and the grams of water in 225 grams of a 8% mass to mass KCl solution. So take a minute, see what you come up with. So we have an 8% mass to mass KCl solution. We want to calculate the grams of KCl and the grams of water to make the solution. And we have 225 grams of it. So first off, we do have 225 grams of the solution. Remember that this solution is made up of two things. One would be KCl, which is the solute. Again, that's the smaller part of the solution. I know that's the solute because that's the name of the solution. So those guys are always the same. I also know water here is going to act as the solvent, and water is a good solvent in this case because KCl is an ionic compound, so they interact really well with one another. So when we talk about the 225 grams of solution, that is made up of two things. It's made up of the grams of the KCl, which again is our solute, plus the grams of water, which is our solvent. So the goal here is we kind of need to figure out, both of these things. And we could use really the other piece of information that was given to us, which is it is an 8% by mass KCl solution. So there's a couple different ways you could do that, but if it says it is basically 8% by mass KCl, that basically means that we have 8 grams of KCl and 100 grams of solution, which we could use as a conversion factor. R in 100 grams of solution, we have 8 grams of KCl. So again, we could kind of take the sort of conversion factor route on it. And we do have 225 grams of solution. So if we take 225 grams of solution, and we use really this kind of conversion factor over here, which tells us that there is basically 8 grams of KCl in 100 grams of solution. The grams of solution will cancel. And if we do that, that is 225 times 8 divided by 100. It gives us 18 grams of KCl. So by using the percent by mass, we've now figured out how many grams of KCl, which is really our solute. So this number right here that we just figured out is this number right there. And now that we figured out how many grams of our solute is present, we could use that relationship from above to figure out how many grams of water is present. So we know that 225 grams of solution equals the grams of KCl plus the grams of water. And now that we know how many grams of KCl there are, 225 grams will equal 18 grams plus the grams of water. Subtracting my 18 to the other side gives me, we got there 207 grams of water in this case. So if we take 207 grams of water, 18 grams of KCl, that gives us a grand total of 225 grams of solution, and we will have a solution that is 8% KCl. Any questions on that calculation or percent concentrations? Okay, so percent concentrations are, again, a very common sort of unit of concentration for solutions. Again, sometimes using them kind of like conversion factors, especially if you're given the percentages, are helpful. You could also obviously plug and chug into the formula as well. So here's just a table, kind of shows what we've been doing, pulling those percentages and making them into conversion factors or useful conversion factors. Again, a very helpful way to sort of approach some of these problems. Now, although percent concentrations are a nice unit of solutions, the most common sort of unit of concentration for solutions is actually molarity. So molarity is really sort of the big unit of concentration. It is the unit it is the unit that we see the most. So let's talk about what molarity is. Molarity is really moles per liter. So when we say molarity, it is moles of solute per liter of solution. And that's really what molarity is. Molarity, again, is often just kind of used almost like a formula. Molarity is moles per liter. And we really could solve for any of these three things. So we kind of want to think of these almost like a formula. So if we wanted to solve for liters, for example, that would be moles divided by molarity. If we wanted to solve for moles, that would be liters times molarity. And those are three really sort of important rearrangements, I guess, equation, or three versions of this equation that we do come across a lot here in chemistry. So what does it mean when we do say we have a molarity solution? So for example, if it says we have 4.50 molar, which is how you pronounce it, big M, sodium chloride solution. It is very important that when you go and take this number here with the units of molarity to do a calculation, I highly, highly recommend that you get rid of the big M and you convert it into the actual units of molarity, which is moles per liter. So what that means is this would be 4.5 moles of case of NaCl. Again, the number stays with the moles and it's always per liter. By using both of those units, which is what big M stands for, moles per liter, you can see both the moles part of the units and the liters part. It is very common that people will sometimes leave it as big M, and as they start to do the calculation, they literally have no clue where the liters is. Should they be multiplying? Should they be dividing? So I would highly recommend that you just automatically sort of convert it into moles per liter. And that way you could kind of keep track of everything in terms of the units and stuff like that. Any questions on that there? The higher the M value or the molarity value, the more concentrated it is. The lower the M value, the less concentrated it is, the more dilute of a solution that you do have. Now, when we talk about a solution that is 1 molar sodium chloride, what does that mean? Well, it means that you have 1 mole solid sodium chloride that has been dissolved in enough water to make 1 liter solution. It would also mean, in terms of the ions that are present in that solution, because sodium chloride is a strong electrolyte, you would have 1 mole sodium ions, and the concentration of sodium would also be 1 molar. So how does this relate? Well, for example, if we have sodium chloride that's in solution, really when it's in solution, because it's a strong electrolyte, it will 100% break apart into sodium ions and chloride ions. So you almost can, if you know the concentration of this guy, which is 1 molar in this particular example, it is a 1-to-1 relationship between sodium chloride and the sodium ion. The concentration of the sodium ion would also be 1 molar. Again, it's basically a 1-to-1 relationship. Same thing with the chloride. It's a 1-to-1 relationship between the whole thing and chloride. It also is going to be 1 molar in terms of the concentration of the chloride. Now, what happens if we have something that maybe doesn't break apart into basically a 1-to-1 relationship? And just to show you really the sort of long calculation of how we go from here to here, let me kind of show you that. We would start with 1 mole of sodium chloride, the entire thing, per liter. And if we do kind of like stoichiometry, it's a 1 mole of this to 1 mole of the sodium ion. For every 1 mole of the whole thing, we get 1 mole of just sodium ion. Moles cancel, leaves us now 1 mole per liter of the sodium ion, which is the same as 1 molar of the sodium ion. So that is sort of the long version of how you do that calculation. The short version is it breaks apart into a 1-to-1 relationship. You multiply 1 by 1 in this case, and you get the proper concentration of the ion. So let's say we had 4 molar calcium chloride, without the extra L in there, calcium chloride. And we want to know what is the concentration of the ions that are present, the calcium ions and the chloride ions. So we could do that by just looking how calcium chloride breaks apart. Why do I want to keep putting an L in there? I'm not sure. So like L on my mind here, I guess. Get rid of that L. Try it again. All right. Calcium chloride, when it breaks apart in solution, we get a calcium ion and we actually get 2 chloride ions in this case. So if the concentration of the whole thing is 4 molar, for calcium, it's a 1-to-1 relationship, which means we would multiply 4 by 1 gives us 4 molar for our calcium ions. But when we look at the whole thing to the chloride, we basically get twice as many chloride ions than we do calcium. So when that thing goes for a swim, we get, again, twice as many chloride ions than calcium. So it's actually twice as concentrated, which means we would take 2 times 4 molar. And really the 2 is where that comes from. And that would tell us that in terms of chloride ions, the concentration of just the chloride ions in this case would be 8 molar, twice as much of the calcium ions. Clearly, when we talk about concentration like this of the ions, they're not additive. Obviously, 8 and 4 does not give you 4, but basically it's the proportion of ions that you get when somebody goes for a swim. If it broke apart into a 1 to 3 relationship, you would take the concentration of the whole thing and multiply it by 3. So that's how we can relate concentration of a whole ionic compound to just the individual ions. Any questions on that? And again, the long calculation for that, which you definitely don't need to really do, the long calculation is we are starting with 4 moles per liter of calcium chloride. From the way it breaks apart, again, it's a 1 to 2 relationship between those. 1 mole of the whole thing gives us 2 moles of the chloride ion. Moles of the whole thing cancel. Again, this is why we're basically multiplying by 2. 2 times 4 gives us 8 moles per liter of chloride ions. So again, that's sort of the long version. The short way of doing it is to just take basically the coefficients and times it by this number, and that will give you the concentration of each of the ions that are present. Any questions on that there? Okay, why don't you give one try here, see what we got going on, maybe. There we go. Calculate the molarity here of a solution that's prepared by dissolving 15.6 grams of KBr in enough water to make 1.25 liters of solution. In case you don't have a periodic table near you, potassium is 3910 and bromine is 7990 grams per mole. All right, take a moment or two and see what you come up with. So obviously we're looking for the molarity, and sort of the full version of molarity is moles of solute per liter of solution. And here, the 15.6 grams of KBr would be our solute, and enough water, which actually would be our solvent, to make 1.25 liters of solution. So we actually have the liters of solution part. We do need to get ourselves to the moles of the solute. That we don't have, but we do have that we have 15.6 grams of KBr. So we should be able to know how to convert that to moles. Again, that is the molar mass that we use to do that. And in this case, it's just KBr, which means we just need to add those together. So the molar mass here of KBr would be our 3910 plus our 7990. And that looks like 119, maybe 3910 plus 7990 gets us 119 grams per mole. That's what we'll use as a conversion factor to take our grams of solute and divide it by the molar mass. Grams cancel. And then we got 15.6 divided by 119. Call it 0.131 moles of KBr. We now have our top part that we need. So the molarity here would be our moles divided by the liters of solution. And we will end up with, looks like 0.105. And again here, the units do not cancel, so 0.105, and you can leave it as moles per liter. Number always stays with the moles part, and it's always per 1 liter. Or if you want, you can at this point just write big M, which stands for moles per liter, and maybe like a KBR in terms of our answer. So you could leave it really as either way there. Moles per liter or big M. That's sort of your final answer. Any questions on that there? Here's just some of those different units that we talked about previously here. Again, our percent by mass, which is our percent mass to mass, our percent volume to volume, our percent mass to volume, and really our molarity, which is big M. And again, that is the one that we do see the most. You typically see it on reagent bottles there. So let's take a look at another one. What is the mass in grams of sodium nitrate that's required to make 202.5 liters of a 0.15 molar solution of sodium nitrate? I'm going to give you some numbers that might be helpful for you. Sodium is 2299 grams per mole. Nitrogen, 1401 grams per mole, and oxygen is 16 grams per mole. So take a little bit of time here and see what you come up with. We're looking for how many grams of sodium nitrate you need if you want to make a 2.5 liter solution that ends up with a molarity of 0.15 molar. All right, so we got a couple things here. We are looking for grams of sodium nitrate. We're making a solution that really has a volume of 2.5 liters and has a molarity of 0.15 molar sodium nitrate. So first off, we can really look at these two numbers here, and more so we can look at this number here. As I mentioned before, very common mistake people make is they leave the big M as they try to do some calculations, and they really do get lost and go, I don't even see any type of volume unit there or anything like that. So when you do have something, again, that is 0.15 molar sodium nitrate, that is the same thing as saying you have 0.150 moles of sodium nitrate per liter. Or you could use it really as a conversion factor and flip it around, a liter on top, 0.15 moles of sodium nitrate there on the bottom. So how does that help us? Well, if you're not sure, you can just think about what molarity is, which is moles per liter. I am given the molarity. I am given the volume. So if you're not sure what you should do, solving for moles would make a lot of sense. And it would make a lot of sense because if you do solve for moles, it's a very quick jump from moles to grams here using the molar mass as our conversion factor. So that's sort of where we're going with this. So we do want to rearrange this. We want to solve for moles, which would be liters times molarity. And again, by separating out that molarity value into sort of these conversion factors, you again could just basically do it like a conversion problem where we could take our 2.5 liters, and just like in a conversion problem, we want to get rid of liters, which means I want to use my conversion factor here on the left, liters on the bottom, 0.15 moles up there on top. And we end up with 2.5 times 0.15 gives us 0.375 moles of sodium nitrate. Again, the nice thing about this is you could clearly see the units and what is canceling and what is not canceling. In this case is moles. Any questions up to that point there? At this point, we're close to what we want, but remember, we don't want moles, but we do want grams. So it is the molar mass that's our conversion factor. To do that, we need the molar mass here of sodium nitrate. So that is a 2299 for the sodium, plus a 1401 for the nitrogen, plus 3 times 16 for the oxygen. Adding all those good things together here gets us 85, it looks like, actually on the nose. 85 grams per mole. We will use that to finish out this problem and get us into the proper units. And that would be 85 grams on top per mole of sodium nitrate. Moles will cancel. 0.375 times 85. And we end up with, we'll call it 31.9 grams of sodium nitrate. Any question on any of those steps there? So what does this really mean? You know, if you were to make the solution, what it would mean is you would want to go to this balance or the scale there. You want to take your bottle of sodium nitrate and you essentially would want to weigh out 31.9 grams of it. You then would want to put in some deionized water with it, enough to give you a total volume of 2.5 liters. Give it a mixy mix, shaky shaky, all that good stuff. Get all the solid to dissolve. And what you should be left with is 2.5 liters of a solution that has this concentration of 0.15 molar. Any questions on sort of what those numbers all mean? Yeah. So take a look at these couple of examples here. We were actually interested in this case. What is the concentration of the ions that are present? So again, as we talked about a little bit earlier, we could actually use the formulas here to help us out. So let's take a look here at the first one. It is 1.2 molar sodium sulfate. And what will help us understand each of the ions and what their concentrations would be how it would break apart. So if I had sodium sulfate, when it breaks apart and is in solution, it's not going to stay together as sodium sulfate. It will break apart into 2 sodium ions, and I get the 2 from here. There's again, this guy goes for this guy. So there's 2 sodium ions plus 1 sulfate ion. Now, what that means in terms of concentration is, again, you can think about it in terms of proportion. So for every one of these guys, I get 2 of these guys, which means if the concentration of the whole entire thing is 1.2 molar, I have twice as much sodium ions. So it would be 2 times 1.2 molar, which would give us 2.4 molar for the concentration of the sodium ions in that particular solution. When we look at the sulfate, it is a 1-to-1 relationship in terms of how it breaks apart, which means the concentration of this guy would be 1 times 1.2 molar, or 1.2 molar sulfate ions. We could see in comparison what we were just talking about, there's twice the concentration of sodium ions as there is sulfate. And again, that is because when you drop this guy into the solution and it breaks apart, you will get 2 sodium ions for every 1 sulfate ion. So twice the concentration of those guys versus the sulfate. Any questions on that there? So looking at the next one. That right there. We have 0.75 potassium chromate. And if we do kind of the same approach, potassium chromate will actually separate into 2 potassium ions plus a chromate. So same idea here. If this is 0.75 molar for the whole thing together, it is a 1 to 2 relationship between the whole thing and just the potassium ions, which means 2 times 0.75 molar gives us 1.50 molar potassium as its concentration. And it is a 1-to-1 relationship between potassium chromate and chromate, which means 1 times 0.75 molar gives us 0.750 molar. Again, we see twice the concentration of potassium to chromate. Same idea. When we dump this guy into solution, the K2CrO4 breaks apart into 2 potassiums and 1 chromate that's flying around in that particular case. Any questions on that one there? So again, sometimes you're interested in maybe just the ions. Sometimes you're interested in the whole thing. And you could kind of do a mole to mole relationship from the equation to figure out, what is concentration of just the particular ions. Again, very simply, if it's a 1 to 2 relationship, you multiply the concentration by 2. 1 to 3 relationship, multiply it by 3. 1 to 1 relationship stays the same basically because you're multiplying by 1. Any questions on molarity or molarity of ions? Now, oftentimes solutions that we get are sometimes referred to as stock solutions, and they're actually very much more concentrated. And we oftentimes will take these more concentrated solutions and go through the process known as dilution to make a more dilute solution. So in often processes, really the only thing that happens during a dilution is you add more solvent. And when you add more solvent, a lot of times water is a solvent that we use. So a lot of times we're just really adding more water, or again, if water is not the solvent, some other thing that is a solvent. So what does that do to sort of our concentration of that solution? Well, if we look at the molarity, that is the moles of the solute divided by liters of solution, when we add more solvent, like water, what we're really adding is this guy right here, the bottom value. Top value stays the same, but we're adding more of the solvent, which will change the volume of solution, which means the bottom number will get larger. So this number gets larger, which means the molarity gets smaller. So really by adding more solvent, we're increasing the volume of the solution. Mathematically speaking, top number is a small number, bottom number is a large number. The molarity will come down. Important to remember, again, we are only adding solvent, which means the moles of the solute, the stuff dissolved in there, before and after will remain the same. So how do we go through this process? Well, there's many ways you could kind of make a solution. One of the proper ways would be to use something like this, which is a volumetric flask. Volumetric means expensive, also means that there typically is just one marking on it. So let's just say, for example, this was a 100, it's actually 500 over there. Say this is a 500 milliliter flask. When you would fill it to this line, that would represent, in this case, 500 milliliters. So typically speaking, you put a little bit of your solute or what you're trying to dissolve in there. It could be a solid, could be a liquid. You add a little bit of water, usually about halfway there, kind of cap it up. Give it a little shake, 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 mixy, mixy. That hopefully should dissolve whatever you have in there. Once it is successfully dissolved, at that point, you very carefully, with your water bottle or something like that, fill it up to exactly the line is where it needs to go. And you should have the proper solution at that point. Now, very commonly when some people use something like this, they're not very careful, and they end up perhaps go with kind of like a blue. They go like up here, a little bit above the line. And they think to themselves, well, I'll just pour out whatever I went over the line. The problem with doing that is at this point, everything that you put in there to dissolve, all the solid, has now been dissolved. And some of that solid is here, your solute. And if you decide just to pour out that excess, you're actually changing the molarity of that solution because you have now dumped out some of the solid that should be there. So it's really important to usually go slow. Usually you can use a funnel or something like that, and maybe a medicine dropper or something like that. But once you're ready to sort of add in what you're looking for here, you want to go really, really, really slow. Make sure you do keep it below at the line and definitely not go over it. Any questions on a dilution? Now there is a formula that helps us sort of calculate what solution we would make in terms of molarity, how we need to make the solution. And the dilution equation is this one, right here. It is M1V1 equals M2V2. This is usually before you do the dilution, so the more concentrated solution. This is after the dilution, so it's obviously the more dilute solution. So when we use this equation, molarity on both sides work. The volume here actually could be in liters, or it's okay to do it in milliliters here if you want. So for example, if we have M1V1 is equal to M2V2, and we're solving for M2. M2 would be M1V1 divided by V2. And if we did molarity for M1, and we did milliliters for V1, and we did milliliters for V2, the milliliters will cancel, be left with molarity. So when you're using this equation, you don't necessarily have to convert, excuse me, you don't really have to convert the volume into liters. You could leave it in milliliters. You can convert it to liters, absolutely. And that's not to be confused, though, if it's not a dilution question. You just simply have volume and you want to use molarity by itself. You do need to definitely convert it to liters so that they cancel. But using this equation, as long as V1 and V2 are in milliliters, it will come out okay. There's also another version of the sort of dilution equation that sometimes people use or see, and that is C1 is equal, sorry, C1 times V1 is equal to C2 times V2. It's really the same deal. Again, most people use molarity, so this is a very common one. But C here just stands for generic concentration. So you technically could put into this equation like those units we saw earlier, percent mass, mass, percent volume, volume, percent mass to volume instead of molarity. But most people will go with the M1V1 is equal to M2V2, again, because molarity is the most common unit of sort of concentration. Any questions on that? All right, so I want to try one here. What volume of 19 molar sodium hydroxide must be used to prepare 1 liter of a 0.15 molar sodium hydroxide? So take a couple minutes to see what you come up with. Let's take a look here and see. So just so everybody sort of visualize what is happening here, maybe. Right, there it is. So basically, you have 19 molar sodium hydroxide. That obviously is more concentrated. So we have this guy bottle sitting here of 19 molar sodium hydroxide. So obviously, the more concentrated bottle. We want to do is figure out how much should we take out of this guy and put into here that we will end up with a total volume of 1 liter, or 1,000 milliliters. And it should have a concentration of 0.15 molar. So that's sort of the goal. And we could use our dilution equation here. We also know it's a dilution because we're not really reacting it with anything. So we're starting with sodium hydroxide that has a concentration of 19 molar. We're ending with sodium hydroxide that has a concentration of 0.15 molar. So the only thing that happened here is the molarity went down, which is typically your indication that is a dilution. We would add some water perhaps to this. So we could use our M1 V1 is equal to M2 V2. Again, this guy is usually the more concentrated ones, the M1 and V1. So M1 in this case would be 19 molar. V1 we don't have. What we're looking for is the more dilute guys, which are on this side, and we're looking to end up at 0.15, and we're ending up with a final volume of 1 liter, or again, 1,000 milliliters. So again, if we just kind of mark off, we are missing V1, which means that makes sense to solve for. So V1 would equal M2 V2 divided by M1, dividing the M1 to the other side. Putting in our numbers, 0.15 molar, 1 liter divided by 19 molar. Molarity cancels out. Because I left it in liters in this case, I will end up in liters. So that's 0.15 times 1 divided by 19 gives me something like 0.00789 liters. Or if I times it by 1,000, 1, 2, 3 places, gives me 7.89 milliliters. What is that? Sort of 7.89, or if we want to round a little bit here, maybe this here. If we want to round a little bit here, we'll take it to like 7.9, since everybody else is to sort of milliliters. What that means is we would go into this bucket here of the 19 molar sodium hydroxide. We would take out 7.9 milliliters of it. So we'll kind of color code here. So we'll call this guy yellow. So we take out 7.9 milliliters of it. And the rest would be water. So the question is, this is sodium hydroxide we would take. How much water should we put in there? Should we put in there 1,000 milliliters of water, since that's our total volume? And the answer would be no, you should not put 1,000 milliliters of water in there, because if you did, that plus the 7.9 milliliters you already put in there would give you a total volume of 1,000 plus 7.9 gives you 1,007.9 milliliters, which is too much. It's not the total volume we're looking for. So very common in dilution problems, they oftentimes will ask you how much water, for example, should you put in there? And there's a very simple way that typically you calculate how much water, and that is the volume of water is typically V2 minus V1. V2 is typically your final volume you're trying to make, and V1 is how much you took out, which means in this case, we want to make 1,000 milliliters of solution, and we already put in there 7.9 milliliters. That tells us that the amount of water we should put in there would actually be 992.1 milliliters of water. So in this case, with the 7.9, we would then fill it up with our 7.9 milliliters, we would put in there 992.1 milliliters of water. 992.1 plus 7.9 gives us a grand total of 1,000 milliliters, or 1 liter, which is what we're looking for. Again, at this point, if we give it a good mix, we should end up with a solution that is 0.15 molar. Any questions on that?
Professor, I have a quick question. How did you determine to not know what V1 is versus V2?
The truthful answer is it doesn't necessarily make a tremendous amount of difference. Most people, though, when they look at the ones, for example, the M1, V1, most people think of that as the more concentrated part. And what that means is when we look at the molarity number, the larger molarity number would go on that side, the smaller molarity would go on the other side. And then obviously whatever volume would go with the larger number would be the V1, and whatever volume goes with the smaller number would be V2.
Okay.
It really doesn't matter. As long as the real key here is as long as you keep the molarity and volume numbers that go together.
Okay.
As long as you keep those guys together on the left side, right side will come out the same mathematical.
Okay.
That's usually how people look at it. The ones are sort of your more concentrated solution, and the twos are your more dilute solution that you're trying to make.
Okay, thank you.
Welcome. Other questions? Okay, so let's take a look at another one here. So take a second here. What is the volume of water that's needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar solution of calcium nitrate? So take a couple minutes to see what you come up with. We're doing, again, we want to make, in this case, 500 milliliters of a 0.25 molar solution of calcium nitrate from a 5 molar solution of calcium nitrate. So again, this 5 molar is more concentrated. So that typically would be our M1. We don't really have a volume that goes with it. We do know that what we're trying to make is a 0.25 molar solution. Again, lower the concentration, more dilute. And the volume that goes with what we're trying to make is 500 milliliters. So again, visually here, we have sort of a stock bottle sitting there that's more concentrated. That is a 5 molar calcium nitrate solution. Again, we're going to take another container here, and we want it to have a total volume of 500 milliliters and a molarity of 0.25 molar. So typically speaking, when you solve for V1, which is the case here, that's basically how much we need to take of the more concentrated solution into our dilute solution. So again, we can use our M1 V1 is equal to M2 V2. Again, the one thing we're missing is V1. So V1 would be M2 V2 divided by M1. In this particular case, we would put our numbers in 0.25 molar. And here, this would be 500 milliliters. If you wanted to, you can convert that to liters, which would be 0.5 liters. Again, it's okay in this particular application to leave it as milliliters, but if you want, you absolutely can convert it to 0.5 liters, whichever way you want to do it. And we're going to divide here by our first molarity, which is 5. And again, the reason we can leave it in milliliters is these guys will cancel, and that leaves us milliliters. Again, if you did in liters, you would end up with liters. So if we do that, we end up with 0.25 times 500 divided by 5. It gives us 25 milliliters. And again, it's important to remember that this is actually, in this case, 25 milliliters of not water, but of the calcium nitrate. And that basically means we're going to go into this first container and take out 25 milliliters of it. The rest would be the water, which is really what it is asking for, is how much water is needed. Again, our total volume is 500 milliliters. So the volume of water would be V2 minus V1. V2 was 500 milliliters. V1 we just calculated as 25 milliliters. That means that we should dump in there 475 milliliters of water with it. So when we would do that, we would put in our 25 milliliters of our more concentrated solution. We would dump in our 475 milliliters of water. Again, if we gave this a really good mixing, we will end up with a solution that has a total volume of 500 milliliters, and it has a molarity of 0.25 molar. Any questions on that? Again, very important to read the question because most people will lay up to 25 and put a box around it. And in this particular case, and in a lot of dilution questions, that's a very common question, is actually how much water you would need to add rather than maybe, the individual volume. Any questions on dilutions or how to do those calculations? Okay, we will stop there, I think, for today. Couple of reminders. Wednesday, there will be no lecture as we are taking exam 2, I believe. And remember, exam 2 will cover chapters 6 through 8. So I'll go off the top of my head on that. I believe that should be some bonding, I believe, some naming, if I'm not mistaken. That should also be some gas laws, I believe, and also balancing equations, types of reactions, and stoichiometry, grams of moles, I believe. That also means, again, that the online homework should be due as well the next day or so. So make sure you complete that. And again, just like last time, it'll be on Canvas. You'll need to use Proctorial. You will be given, obviously, a periodic table, some conversions. Again, you will not be given any of the geometries or polyatomic ions like we talked about previously. And it will open part multiple choice where you don't need to show work. And there will be a part where you will need to show work and upload your work after you submit your exam immediately. And again, it will appear probably at the very top of the module section. And I'll open it probably like I did last time. So I'll open it around 5 in case you want to kind of start a little bit earlier and don't have to rush maybe to lab or discussion afterwards. Again, just like last time, if you start a little bit earlier, you don't get any more time. You get the same time if you start at 5 or if you start at 5:30. But you definitely shouldn't start much later than 5:30 if you want all the time. Again, if you start much later than that, then obviously you get whatever time is left at that point. There will be an announcement that will come out like normal that says the exam is open with a link directly to the exam. And just like before, you need to kind of go through the different parts of the module. After you do the agreement there, that will open up your exam. After you submit your exam, then the assignment where you can upload your work will be uploaded or open at that point as well. Any questions on any of that?